This is October-November 2024, paper 1-2, physics 5054. Now, in order for you to get an A star, I've recalculated this, you need to get at least 60 marks out of 80 when you're preparing this at home. This is your target. Out of 200. Total this 80. This equals 160. We convert it to 200. Came to 200, so these are marked out of 200. If I think you go back to 160, they will be down to 127, or I guess 130. It's the percentage. But anyways, that's your target for an A star. Let's resume. So we have October-November 2024, paper 2-2, and this is physics syllabus code 5054. This is O levels. Okay, a jet ski is a type of boat. Okay, fine. Let's quickly go through that. So he says he's traveling fast, high-speed jet of water from the back, out of the back of the jet ski. Okay, so complete the word equation. Now, the word equation given in the marking scheme is increase in momentum, but I believe that you can easily use the change in momentum. So this would be change in momentum divided by the unit time or time taken, or as the marking scheme suggests, the definition is increase in momentum. Of course, you will write down the full words. I'm just skipping this through. Divided by the unit time. He says in 2 seconds, that's our time. That's our mass, and this is our velocity. It changes from 0 to 30 meters per second, backward force exerted, so that will be F equals to change in momentum divided by change in time. So the momentum is changing with a mass of 180 from a speed of 0 to 30, so that will be 30 minus 0, which eventually becomes 30, divided by in a time frame of 2 seconds. So when you calculate this, eventually you're going to get a full value of 2700 newtons. Then you go on to the next one. Using Newton's third law, he says explain. Now, this is a common question. This is a repeated question. This has been asked in the past in terms of a swimmer pushing against a wall. So how do we justify this action and reaction pair? So you will tell, or you will write down that the pump increases the momentum of the water by pushing it backwards. Now, when you push the water backwards, the water exerts, or the water applies a force on the jet ski in the forward direction as a reaction, which pushes it forward as a result, and the jet ski moves forward. It's as simple as this. For example, if you are standing near a wall and you have skaters, or you're standing on a skateboard, if you push on a wall in this direction, you go in this direction. Why? Because the force that you applied on the wall has been applied back on you, but in the opposite direction. The student has a mass of 70 kilograms and the jet ski has a mass of 280 kilograms. Use your equation from A2, which we've written down, to find the force acting. Okay, fine. So that will be F equals to ma. Yeah, that's the acceleration. So that would be, and he mentions to use the equation in part A2, which should be this. Yeah. So since we were dealing with the change in momentum, that would have been mv minus mu divided by t in reality. So he's actually talking to you about using the F equals to ma per se. So this will be, or using the values, your answer from A to, yep. So 2700 equals to mass. Now this will be a bit confusing. You might by mistake put only the mass of the person or the jet ski. Since they're both moving in the same direction, they're both experiencing this force. So it will be actually 70 plus 280 into acceleration. Again, that's a combined mass at this situation because they're both moving in that direction. When you take this to the other side to divide this, this will be 7.71. Your answer becomes 7.7 up to 2 significant figures. The jet ski reaches 20 meters per second. Calculate the total energy. So this will be half mv square 1 over 2 into mass in the current situation of both objects will be 70 plus 280. So that becomes 350 into the velocity is 20 square. Don't forget the square. This is where you get it wrong. And your final answer will come out as 70,000 joules or joules. So this will be 70 into 10 raised to power 3 or 70,000 or 7.0 into 10 raised to power 4, whatever suits you. Question number 2. A glass beaker of mass m rests on the horizontal surface as shown in the beaker or shown in the glass in this image. He says the beaker exerts a pressure on the horizontal surface. This is a repeated part, but it's explained in the book. You might not find this in the past papers, but one of the examples was in the book. So he said the radiuses R determine the expression in terms of the gravitational field strength, m, g, and R for the pressure. Now, pressure is equal to force over area. My simple question would be, who is exerting the force in this situation? That's generally the weight of the object. Even you are exerting of pressure on the ground you walk on. And where does the force come from? It's your own weight. That's the mg part. So force, in this case, is because of the weight, so that will be the mg. And the cross-sectional area is wherever the base touches wherever this beaker's base touches the base. So we can find this by using the formula. Because it's a circular container, we can use area as pi r square. So to present your data, what you can do is simply write down that the force in this case is actually equal to mg, or weight, and then equals to mg, or area is equal to pi r square. You present your data like this, and then write down the formula as force divided by area equals to mg divided by pi r square. That's how you present your paper. That's how you present your data. And this is the equation in the answers. He says this is how it is being filled up. There's a container X. There's a horizontal surface. Okay, fine. He explains the situation that at time t equals to 0, the tap is open, which means that it started at time t equals to 0. These timestamps that the examiner tells you is actually in terms of what this situation might be. At time t equals to 0, it always means that at the start or at the beginning, nothing was happening before that. At time t equals to capital T means something has taken place at this point, and this could be any arbitrary value. Let's say 15 seconds, 20 seconds, 25 seconds. It really doesn't matter. But in terms of the event, something must have happened at this time. That's why he's mentioning this as capital T. Now it says sketch on the graph 2.2 show how the pressure exerted on the horizontal surface varies with time t 0 to 2t. Now the first things first. First, let's what I used to do is draw a dotted line at these two timestamps so it makes the diagram look more accurate and presentable and is easy to follow. So what's happening while the tap water is entering into the beaker? And mind you, he says that it is moving, I think, at a constant rate into the container. Yeah, so probably flows slowly into the beaker, which means it's flowing at a constant rate, and no water is splashing out of the container. That's what he means at this point. So what's going to happen? So always use a formula for the sketch. So the formula right now, pressure is equal to force over area, which becomes mg divided by pi r square. Now notice, what are you changing in this equation? Is the value of g changing? No, it's not. It's always going to remain 9.8. So it's a constant. What about the value of pi? It is also a constant in these given circumstances. And what about the value of r? The beaker stays the same. Whatever radius it has, it stays the same. So really, the only thing that we are changing at the moment is the amount of liquid inside the container by adding it from another liquid. So by the end of the day, the equation that we get is pressure being proportional to mass. You keep on increasing the mass, the pressure increases mathematically. Now, this idea is important because this tells us that the power on both variables is 1, which means it's going to be a straight line. This is going to be a straight line. For example, if it had been another equation in which, for example, we deal with electrical power, it would have been P equals to I square R. If I was drawing a graph of P with I square, then I would definitely be worried by this square. And you've done this in mathematics as quadratic equations. Let's say y equals to x square or 5x square. You know it's going to be a parabolic equation or parabolic graph. So the graph goes like this with current as amps. This is why it is important to have an equation backing before your graph or before you try to draw the graph. And this is why the marking scheme doesn't generally make sense to the students when you're reading them. How do we know there's going to be a straight line? This is how we know it's going to be a straight line. And you can use this technique going up to A levels. Now, the other thing we need to be careful about is this, that the beaker also has its own weight. It also has its own mass before adding the weight, before adding the water in it. If you by mistake start from the origin, it means that there was no pressure being exerted on the floor or on the base at the beginning. You see, the beaker also has some mass. So it should start from a non-zero value. Why? Because the beaker also has some mass. You keep on increasing the mass because you're adding liquid, so the pressure increases linearly, and it is going to be a straight line as explained earlier, because the power on both equations is 1. Now, after time t, he says that at time t, the liquid stops flowing, which means that whatever liquid or whatever amount there was going to be, it's already present. Is there any more liquid being added in it? No. So when there is no more liquid being added together or added in it, it means that the value of mass has now become stagnant. It has now become constant. It's not changing or increasing. So even if the time is passing by, are you changing the value of mass, or are you changing the value of mg in any sense? You're not. So that is why it's going to be a straight horizontal line, because nothing is changing and the pressure during this time remains constant. Because time is moving on, your pressure's value is not changing. That's the shape of the graph. Remember, this is going to start from a non-zero value, and keep an eye for this or these type of questions in the future. Question number 3 is conduction, convection, radiation. He says the door closes, the freezer switched on, a liquid cool is in the pipes, cold liquid flows through the pipes so that it can cool down to the rest of the things in the system. He says explain how the temperature of the rest of the air in the freezer decreases. He's asking you how it cools down. And this is a very standard response for fridge, refrigerators, even heaters. So the cold air will fall down and hot air will rise up. This is a very basic understanding, but why is that happening is more important. So explain why and how. So the volume of the air near the pipe decreases. Why does that happen? Because when you decrease the temperature, the speed of the molecules decrease, and as their speed decreases, they start coming close together as contraction, as we generally know as contraction. When that happens, according to the formula of density equals to mass over volume, you're decreasing the volume, keeping the mass constant, because we're still looking at the same number of particles. Your density increases. If the density increases, that air that is close to this region, that is close to these cool pipes, will become heavier. As it becomes heavier, it starts falling down. It starts sinking. Now, before this step, whatever warm air or warmer air was present in this location will be replaced by this heavy air sinking down, and this warm air will be pushed upwards because cold air is trying to replace it, or is replacing it in the process. The hot air rises, cool air comes down. The hot air that rose now encounters the cooling pipes, becomes cold itself, cools down, comes down, and then the cycle repeats itself over and over again until there's a temperature or thermal equilibrium. So the density increases. This is what we write down for the examiner. The cold air sinks, that is important, and replaced by warm air below. Sinks down and replaces, it would be replaces the warm air below. This sets up a convection current and the whole space becomes cool. Also, if you would just add that the warm air rises and cool air falls, that would also improve the answer even further. And writing down that the convection current is set up is also important. All right, moving on to part B. He says thick insulation 3.1 made from plastic material. He says how plastic conducts or is going to provide thermal energy transfer. Although he mentions it is an insulator, but do insulators provide thermal conduction? Yes, they do to some extent. Not with a 100% guarantee of it very efficiently, but they are still conductors. So particles vibrate and collide with the neighboring particles or with the nearby particles, and they transfer their own energy to the next one. And that is how they move energy from one point to another point, or thermal energy from one point to another point. One thing to keep in mind is that in contrast, if you talk about, let's say, metals, now he's mentioned that there is plastic. He's using plastic for this case. What about if he had mentioned, let's say, iron, steel, copper, aluminium? He will not say that he's using a conductor. He will not say he's using a metal. He would generally name the material that he's trying to use. So you need to identify that that is going to be a metal. And metals have not only particle vibration, but also free electron movement, which helps the conduction, which is why conductors are better conductors. Or, for example, the metals are better conductors of thermal energy, not only just electricity, but also thermal energy. And he says plastic also contains large air bubbles. This is why we wear clothes. This is why we have jackets. This is why we have warmers. They trap air that's close to your skin and do not let it escape. Now, since air cannot escape because you're wearing a warm cloth or you're wearing a jacket, whatever your body radiation or whatever your radiation coming from the body has heated up the air around your body will stay there. That's why you feel warm. So the air is a bad conductor, again stating a fact, then link this with a reason. The trapped air prevents convection current or convection to occur, which eventually prevents the loss of energy or transfer thermal energy. Hence, it becomes an insulator. Question number 4. A large syringe shown nozzle by wax. There is a piston inside the syringe. Okay, fine. That's a common question. He says that the pressure inside the container is this much at this current volume or at this current situation. He says that the cross-sectional area of the piston is this much. What does that mean? It means that the cross-sectional area like this in circular movement or in circular fashion is actually 3.5 into 10 raised to power minus 3 meters square. And meter square is a unit for cross-sectional area. So the friction between the piston and the syringe is negligible. This is important because this point will become a problem or challenge in the next part, in the incoming part. So he said calculate the force on the piston. So we know that since he's dealing with pressure, force, and area, I will need a formula that links all of them. So pressure equals to force over here, bring area to this side. So force equals to pressure multiplied by area. Now we have our equation. Let's replace the value. So this will become pressure, which is 1 into 10 raised to power 5, given by the examiner. And the cross-sectional area, which is 3.5 into 10 raised to power minus 3. The force in this situation comes out as 350. The force comes out as 350 newtons. Very simple, straightforward question, no problem at all. It says the force on the piston A1 acts to the right. So the air molecules inside the syringe are bouncing with the balls, and they are exerting a force in this direction because of the air molecules that are present inside. He says explain why the piston does not move to the right. Why is it not doing that? Now, to put into plain perspective, not just the air inside the container, but there is also air outside the container, which is atmospheric pressure. Now, if you want to go a bit deeper into the understanding, why is it still not moving? You would realize that the air molecules or air particles are colliding with the surface and exerting pressure like this on the entire surface of the syringe, even on our bodies. On this point, on this point, on this point, on this point, this point, this point. Every tiny surface you can think of, air molecules are exerting pressure. But why is it not successful in doing so? You see, if you realize, all of them are being cancelled out. Why? Because the pressure inside the container is 1 into 10 raised to power 5. The pressure outside the container is also atmospheric pressure, which is 1 into 10 raised to power positive 5 pascals. But why is it not successful? The resultant forces or the resultant pressure, but it's better to say resultant force, is actually cancelled out. You might notice that there is one force that does not appear to have anything other, or does not appear to have another component that is going to cause cancellation. You see, if the air molecules are causing this to apply force in this direction, there are also air molecules causing force in this direction. So this cancels with this cancels with this, or this side cancels with this side, and this side cancels with this side. So all these directions are cancelling out. At the end of the day, you're left with only these factors that are trying to or should push the syringe inside, but they are not able to do so. Why? Because the pressure inside is equal to the pressure outside. It's exactly the same surface area being experienced. Hence, there is no resultant force, which is explained over here in this case. I've overcomplicated this for your understanding, but we can just simply write this down in this manner. So pressure from the atmosphere or the atmospheric air outside the syringe is equal to the pressure inside the container, which means that the forces cancel each other out. Hence, they are in equilibrium. No net force is experienced. Hence, it does not move. Question number part B. The piston is now pulled to the right by an additional force. Okay, we're doing this deliberately by force. The temperature of the air does not change, which means we are only going to think about Boyle's law, which is pressure inversion proportional to volume. Explain in terms of particles why the pressure of the air in the syringe decreases. Now, I've seen students write Boyle's law as the reason. Now, be advised, Boyle's law is not the reason. It's actually an observation. You saw this happening. But does that explain the reason behind things? No, an observation does not explain why it is the way it is. So this will be a wrong answer. Don't involve this in your reasoning. The reason is something else. But you can use this to explain or at least state what's happening. So if you pull it towards the right side, the volume increases, so the pressure should decrease. But is this something special in our answer? He's already mentioned why the pressure in the air syringe decreases. He's already answered this part because he knew from the previous past papers this is what students do. So what can you write down now? You explain the reason why this is happening. And the reason is really simple. You start with the increase in volume, that as the volume increases, this increases the space between the gas molecules. They are now moving away from each other because there is more volume. And as that happens, there will be less frequent collisions with the walls of container. This is why gas pressure exists, collisions with the wall of container. Now, since they're colliding less frequently, because they're so further apart, the pressure, the force on the wall decreases, hence decreasing the pressure. So it's a chain of thought. So pressure equals to force over area. We said that colliding less frequently because they're very far apart. They have to cover a long distance. When the force decreases, pressure also decreases. And avoid using Boyle's law as your answer. It's an observation, not a reason. Calculate the pressure of the air. So this will be, again, Boyle's law, P1V1 equals to P2V2. So pressure in the first scenario was 1 10 raised to the power 5 multiplied by volume was given to us in the question, I think. Yes, meter cube. So this is my 1.2 minus 4. So 1.2 into 10 raised to the power minus 4 equals pressure 2. This is what I want to find out quickly. And this is my new volume as 1.5 into 10 raised to the power minus 4. So pressure 2. Now, since I know it is being pulled out, I know by Boyle's law it is being pulled out, the volume has increased, so pressure should decrease. Now, this is used for prediction. Okay, mentally you can predict whether you should expect an answer greater than this or smaller than this. I am predicting that I should expect an answer smaller than this. And would you look at that? If you calculate this, your answer comes out as 80,000 pascals, which up to, or in the standard form, becomes 8 into 10 raised to the power 4, which is less than 1 into 10 raised to the power 5. So again, I don't have to recheck my answer because my prediction is correct. Question 5. Draw a diverging lens. So the diverging lens looks like this. 1 mark question, very straightforward. This is the question given to you. I'm sure you might have read this question before. And you are here to see what could be the problem in your diagram, or did you draw the diagram correctly or accurately? A few things before moving on. These are the focal points. So any line passing through the lens will pass through them. You have to make sure of that. You will do that. The examiner wouldn't come and help you with that. This is your job. So everything is here in place. Let's see what the diagram looks like, what the question states, and let's see what the diagram is. He says the height is 2.1. It's at 3 centimeters. What's the focal length? You can do this by counting the boxes, then draw with the object 2 rays, then another arrow. So I'm going to show all of these parts all at once. This is what your diagram should look like. Let me just zoom out for a bit. This is what it should look like. Now, in that part, he hasn't mentioned to draw all of these lines. You see, for one part in which you have to draw 2 rays, this ray number 1, ray number 2, and ray number 3. You can draw any of the 2 rays from these 3 rays to represent where the location of the image would be. Again, choose 1, 2, 2, 3, or 1, 3. Your choice. The second mark for this part, in this question, he says draw 2 rays. This is what I'm talking about. And then another arrow to show where the image is. So you don't have to draw all 3, but you only draw 2 out of these 3 options. I've done this for you guys. So the third mark would be for making the image itself. Wherever you see the point of intersection, this is where your image will be, and you draw it with a straight line going back, touching the principal axis. One thing that I would like to show that you don't have to do is mark these points. I've done this during the counting process. You don't have to do that. Also, notice one more thing. If I zoom in a bit more, you would realize that I'm actually making sure deliberately that the lines through the lens are actually, this is better. So the lines through the lens are actually crossing from the center. I've brought them to the center and then I've bent them. Don't bring them to the surface and then bend them. That would be wrong. Or don't bring them to the end of the surface and then bend them. The examiner is looking for this. And if you try to make sure that you come to the center and then bend them, your paper not only gets elevated for an A star, but it also will be considered for a distinction. And I've already made sure that 2 of my students got one. So I probably have an idea how to get one. So I would advise you to follow these rules. Now, This is what your diagram should look like. Your arrows should be there. Make sure that arrows are there. And the counting method is also given to you, how to count them, how many boxes to count. So if it mentioned to calculate your focal length, I've actually counted the number of boxes leading up to this point. So that's what it is. Okay. Right. Then he says the focal length. Of course, I've counted the boxes, and the focal length in this case came out as 1.8. Sorry. It came out as 1.8 centimeters. And then we've done this part. We've done labeling O. That would be over here. This is how we've done that. And then he says draw two rays. I've shown how to do that. Then using marked, calculate the magnification. So the formula of magnification, again, some students ignore this, is height of the image divided by height of the object. So the image as I count from my diagram is this height. I've counted the boxes based on this scale, and it comes down to 3.1. So according to my image, this is 3.1 centimeters. The height of the object was given in the question as 2.1 centimeters. 2.1 centimeters equals to, for my case, that comes out as 1.476, which becomes 1.5. Now, the examiner has given a range of answers. I think it goes from 1.2 to 1.8 in the marking scheme. You might have gotten any, but you will still get a credit for this. So don't worry about too much about the accuracy of the lines. Explain whether the image is real. So the image is real. Why? Because rays or light rays from a converging lens, when intersect, make a real image. Question 6. He says, by referring to 6.1, explain the effect of current passing through A and B. And this is the structure of a relay or a magnetic relay. So when the current starts flowing through the coil becomes magnetized. And the coil is going to look like this, of course. It will have a north pole and a south pole. And of course, it will cause induced magnetism on the switch because it's generally made out of iron deliberately because we want it to be attracted to the magnet. So it gets attracted, closes the switch, and then this circuit becomes active. So this is what we had to explain. He said we would say that the current in the coil magnetizes the coil, which attracts the relay switch, which is made out of iron, and closes the switch. This is how it works. Shows circuit linked with the relay, 40 watt of a heater. The switch S is closed, which means you're closing this switch, you're completing the circuit. The variable resistor is adjusted so that its resistance R increases from 0. So this resistance increases from 0 up to, let's say, 500 ohms, 1000 ohms. We do not care. What we do care about the fact is that when you increase the resistance, the current through the circuit starts to decrease. And at a certain point, when the current is too low, it will weaken the coil magnet in the coil. And if it is becoming weak or becomes weaker, it will no longer be will be able to attract the switch from the other side. And if it's no longer able to do that, the switch opens up and the heater switches off, which is the answer for our next part. He says that explain the behavior of the graph when RH is reached. Again, the value of RH, we don't know. It could be any other value, but whatever value that is, it is so high, or the resistance at this point has become so high that the current is no longer producing a strong enough magnet, which will not be attracting the switch towards itself. That's how we explain it. That's what we're going to explain. So initially there is high current because the resistance is 0 in the coil, which kept the coil magnetized. You can pause the video and read it for yourself. And the switch S remained enclosed, keeping the heater on in the closed position, keeping the heater on. At this location, at this point, as R is increased, the current decreases, or reducing the strength of the magnetic field of the coil. It is not strong enough to hold the switch S in a closed position at this moment. It opens and disrupting the supply to the heater. Hence, the graph shows an abrupt reduction of power to 0 watts because now the switch has opened. This has stopped working. If the circuit was drawing, let's say, 40 watts of power, it's not drawing any power at this moment, so it goes down to 0 watts. The 40 watt heater connected to the 12 volt supply switched on. Calculate the energy transferred. So power equals to energy divided by time. Energy equals power multiplied by time. power is 40 watts multiplied by time is 2 minutes, but minutes have to be converted into seconds because we're looking at energy in joules. So for joules, it has to be in seconds. Unless the question is about kilowatt hours, you will never convert time into in hours for any calculation of power. So when you do that, the answer comes out, I think, it comes out as 4,800 joules. Yeah. So this is 4,800 joules. Let's move to the next part. Okay, the resistance of the heater. Now, there are multiple ways of doing this. I suspect it's a 3-mark question. He wouldn't let us off with an easy one, but let's see. So you could have used P equals to IV, but you don't have current. So what would you do for current? So you would use Ohm's law, which is V equals to IR. The voltage of the heater is 12 volts, and the current we don't know. The resistance is what we wanted to find out. So how do you find the current? No, first you will use P equals to IV. So, yeah, sorry. So first you use P equals to IV. So we have 40 watts of power. Current is not available to us. So voltage, it is operating at 12 volts. So the current comes out as 3.33 amps. Then you use V equals to IR. 12 volts equal to current, which is 3.33 into R. R comes out as 3.6 ohms. Now there's another way to do this, a very straightforward one. I'm not sure why he didn't let you do this one, but it's very straightforward. That will be P equals to V squared divided by R. The power is 40 watts. The voltage at which it is operating is 12 squared divided by R. You bring R to the other side and 40 to the other side. This becomes R equals to 12 squared divided by 40. This also gets you 3.6 ohm. If I was your in position, I would be doing this one. It saves time and it's much easier. Question number 7, frequency of an alternating main supply with 50 hertz signal and 300 volts. Sketch the AC supply. This has been a really common occurrence by the examiner. It has been repeated again and again. So first of all, what I would do is use a lead pencil for the graph, and very lightly I would draw on the graph and mark these boundaries for myself. Again, you can do this without this, but then again, it's a technique that I've used for myself, and I've explained to the students who have scored good grades in the past. So 50 hertz. What do you do with 50 hertz? So 50 hertz, F equals to 1 over T. To find T, because this axis has time period, I cannot use 50 hertz directly. I can use it indirectly. So this will be 1 over 50. This becomes 0.02 or 20 milliseconds. No need to convert it in this way because the scale is already given to you in seconds and not milliseconds. So the 0.02 means one complete wave. So one complete wave expected here, one complete expected here, and half a wave expected here. Now just halving the time scale, because I know that in first half it should be positive, then negative, then positive, then negative, and so on and so forth. So in a way, I have made these coordinates so I know where to cross them. So first coordinate here, then here, then here, then here, and then here. And then I would erase these lines again for myself to draw the graph when I have to draw the graph. I would practice before drawing the graph or passing through these points one time before drawing the actual graph. So the graph should look something like this. Again, it's not going to be very smooth, but I will try to make it to the best of my abilities. This is your final answer. You're touching 300 volts, which is our peak voltage for the sine wave. We have made sure that we have incorporated 50 hertz by one way or the other. And you will see in the marking scheme, he says that there should be 2.5 wavelengths or 2.5 waves. This is wave number 1, this is wave number 2, and this is the next half wave. From here to here, 1, 2, and 2.5. This is what it means. Part B, he says, there are 750 turns on the primary side and 60 turns on the secondary side. This primary side is receiving 300 volts because it's part of the same question. The core of the transformer is made from iron. Why? Because it's a temporary magnet. It is easy to magnetize and demagnetize. Explain why there is a voltage across. Now this is again a repeated question. Please memorize this answer. It is from the heading or from the topic, that is working of a transformer. How the transformer works. These are free 3 marks. Please don't avoid them. So The alternating voltage in the primary coil causes the changing magnetic field in the core. This changing magnetic field cuts the coil, this is coil, of the secondary side and induces an EMF on the secondary coil. Inducing EMF is very important. Now, from these two lines, it actually goes or dives into Faraday's law. Again, you provide alternating current or voltage in the primary coil. The current goes in, then comes back, then goes in, comes back. This causes a changing magnetic field. So this is, let's say, north and south. In one sense, in the next half cycle, this will be south and north. Because the magnetic field is always changing, sometimes over here, then here, then here, then here, the magnetic field in the core is also changing at all times. This changing magnetic field, when reaches the secondary coil, or when is experienced by the secondary coil, also experiences induced EMF because of Faraday's law. Faraday said that any conductor experiencing a changing magnetic field will produce voltage, will produce the induced EMF. This is how secondary coil gets voltage. And every transformer works like that. So the secondary turn has 60 turns. He says, what's the maximum voltage on the output? So this will be number of turns on the secondary divided by number of turns on the primary equals to voltage of secondary divided by voltage of primary. All the values are given to you. Number of secondary turns are 60. Number of primary turns are 750. Primary voltage is 300. You take this to the side, multiply this, and the secondary voltage comes out as probably 24 volts. Yeah. So this is 24 volts. You write this down over here. Question number 8 is from Radioactivity. It says, describe the structure or composition of alpha particle. Now this is new in terms of answering the question. You see, previously he would accept that it's 2 protons and 2 neutrons in a nucleus. But this time he's enforced that mention and state, or students should state, that there is no other particle involved. Why? Because the misconception is that they think that probably electrons are present on the outside. It doesn't have an electron or electron shell. It doesn't have. It's only 2 protons and 2 neutrons in a nucleus moving at high speed away from a radioactive source. And it has a similarity in terms of composition to a helium nucleus. Saying nucleus is important. Just writing down helium doesn't make any sense. Helium what? Helium gas, molecule, atom, particle, nucleus, electrons, what? So helium nucleus is important. Then he says, deduce when thorium-230 releases an alpha particle or alpha decay, what happens to radium in terms of its number of neutrons, number of electrons? Now this is a good question in terms of writing the decay equation. I would advise you to write down the decay equations, which will become TH 230 in 90, decaying to become radium, which is Ra. What do we get here and here? We don't know, but we do know that alpha particle is 42. Don't try to do this as a shortcut. You know that you have time, so you can do this properly. This will become 226 by 230 take away or subtract 4. 90 subtract 2 or take away 2 would become 88. This is what the question is about for the second part, to calculate the numbers 4. So let me write this down over here. So radium is 226 with 88 proton number or atomic number. He says, what's the neutrons? So to calculate neutrons, this will be 226 minus 88. So 226 minus 88 gives us 138 for radium. And then he says number of electrons. Now, you can calculate the number of protons because it's 88. How do you do the calculation for electrons? You see, there's one word in this system that tells you what that is. There is one word, I think, yeah, the neutral atom. When he says neutral atom, it means the number of protons will be equal to the number of electrons. There is no positive or negative charge on it, which is why I have the guarantee that I can use 88 as the number of electrons. I can use it straight away. He says thorium has a half-life of 75,000 years. At the beginning, they had this many number of particles. At the end, it has this many. There are multiple ways to do this. I'm going to show you both of them. So first technique is just a hit and trial. You can start with 7.2 into 10 raised to the power 16 and halve these values yourself and show the examiner the way I am showing that this is how and this is what I'm thinking. Now, how many times do you actually halve? You see, dividing this with 2 gives this, dividing this with 2 gives this, and dividing 2 with this with 2 gives 9 into 10 raised to the power 15. You keep on dividing these atoms by 2 because we are calculating half-life, and this is what half-life is. You keep on doing this until you get your stopping criteria, until you get what you were looking for, until you get the ending. The ending in this case is mentioned by the examiner that this is where we are at right now, today. Now then you count how many times you had to halve. So you had to halve 1 time, 2 time, 3 time. So I can say that it took 3 half-lives. It took 3 half-lives to get from 7.2 power 16 to 9 into 10 raised to the power 15. The time for 1 half-life is 7,500 years. So the total time taken for this whole process would be 225 into 3 zeros. That's one way of doing that. The other way of doing that would be, again, more logical and more mathematical, is to take a ratio. So 7.2 into 10 raised to the power 16 divided by where are the atoms now, or how many atoms do we have today? That will be 15. This comes out at 8, which means that they have reduced 8 times. Now, when you see 8, a good student who has practiced many, many times or has had a lot of practice would realize that this is actually 1 by 8, or it is actually 1/8 of the original, right? So this is, and how do you get this? You start from 1, make it half, then divided by 2 gets 1 by 4, then divided by 2 gets 1 by 8, which means that it has went through at least 3 half-lives, okay? Or some students actually write it down like this: 1 into 2 raised to the power 3 whole power, which means that 2 raised to the power 3, which means that n is equal to 3. That's another mathematical method to do this, which means that these are half-lives. And again, they end up multiplying 75,000 with 3. What the examiner wants to know is an evidence that you have evidence for 3 half-lives, your deduction for 3 half-lives, and you've done this multiplication, and your final answer. If you show it by method 1, it's a bit easier to visualize. If you want to show it by method 2, be my guest, your choice. Part D. He says he's emitting gamma radiation, or thorium-230 is also emitting gamma radiation. Does anything happen to the gamma radiation? Does it respond to electric field or magnetic field? It doesn't. Go straight ahead. Use a ruler to draw these lines with pencil. Question number 9 from Cosmology and Space Physics. He says the radius of the Earth is this much. It orbits every 24 hours. Okay, fine. The radius of the axis is given. He says calculate the speed. So the orbital speed, the formula is given to you in the course, is 2 pi r divided by time t. So 2 into pi into r. The radius of the orbit is given to you, or the circumference. The radius of the Earth is 6.4 into 10 to the power 6. Divide this with time. Now what's the time? It takes 24 hours to do this. So if you were standing at this point, after 24 hours, you would come exactly back to this point. So that's why we're using 24 hours for our speed. So 24 into 60 into 60. How do I know it is supposed to be in meters per second? Because I'm looking at the unit of the question. In the answer, it says meters per second, so I have to convert these hours to seconds. When you do that, this comes out as 465 point something meters per second, which up to 2 significant figures becomes 470. It's explained why the speed Earth decreases as the distance of the object from the equator increases. You see, he's saying that a person standing on the equator will have a different speed as opposed to a person standing a bit further away. The person who's standing a bit further away has smaller circumference. If you can't visualize it from the lower side, let me show this from the top side. What about a person standing here? The circumference or the length of path it is covering is actually this much. It's smaller than the distance of the equator itself. It's much smaller. Now, in terms of the formula, which is V equals to 2 pi r divided by t, are you changing the time for that person who's standing on the other side? You're not. Are you changing 2 pi? It's a constant. You're changing the radius. If you decrease the radius, the speed also decreases, because it has to cover a shorter distance in the same amount of time or a bit longer time. That's why even if it travels at a lower speed, he will still be successfully coming back to the same point after 24 hours. So circumference decreases while the time remains constant, which is explained by the mathematical equations 2 pi r divided by t. We're not changing anything else other than the radius. This decreases, so the speed decreases. Hence, the orbital speed decreases. The Earth moves around the Sun, state which provides this force. That's the gravitational attraction due to the Sun. Again, that's due to Newton's law of gravity. You can do your research on this. I also have a video on the playlist in the GCSE O-level spec. The orbit of the Earth around the Sun is an ellipse. What does that mean? It means that if this is the Sun, then the orbit of the Earth is somewhat like this. It's not perfectly circle. So at some places, the Earth is very, very far away. And in some places, the Earth is very, very close. In these locations, the Earth is close. In these locations, the Earth is further away. That is what an ellipse looks like. So he says, describe what happens to the magnitude of force. Not speed, not acceleration, but the force. on the Earth as it moves in the elliptical orbit. So you have to explain both situations, when it's far away and when it's close. So according to Newton's law of gravity, and it's a common understanding, if you move away from an object or object of mass, its gravitational attraction on you or at that level decreases, which is why if you go away from the Earth's surface into space, the gravitational attraction of the Earth on you also decreases. So based on this idea, because of Newton's law of gravity, we will say that the force changes. And how does it change? When the Earth comes close, it increases. When the Earth moves away, it decreases. It's all down to the formula for gravity, or gravitational attraction, which is Fg equals to Gmm over r squared. The formula is from A levels, no need to worry about this. G is a gravitational constant. And the part we are interested in is the inverse relation to the r. It's the distance. If you increase the distance, the force decreases, because you are going out of reach of the gravitational field of that object. Explain why the Earth travels slowest when it's the furthest distance from the Sun. It's mostly related to the exchange of gravitational potential energies. You see, what happens if you throw a ball upwards? What's happening in terms of the energies? It has kinetic energy when it leaves. It has gravitational potential where it goes some height. And at this point, it is generally zero kinetic energy because it starts to come back down again. Similar thing happens here. So the gravitational potential energy is very high when it is further away, which is why it is moving at slow speed, because at this point, the kinetic energy store is low. It's an exchange between the two. And at the further distance, hence the kinetic energy is low, meaning the speed is low. Or vice versa, you can use the same argument on the other side.